Thanks everyone for joining us here. Again, Balian's kindly volunteered to provide the project team with an overview of SimCCS and perhaps some of the modules within the program as well. We agreed that this was probably important as we move forward here through task 4 and we start talking about commercialization and looking at pipeline networks. And again, this will obviously feed into some of the work that our other project partners are hoping to accomplish, looking at techno-economic analysis and things of that nature as well. Before we get started, just some broad project kind of information here. I know we haven't hosted a formal project meeting here recently, but I have been in contact with the project leads for our upcoming 2022 deliverables and milestones. And we've established kind of a workflow and tentative dates for those reports as well. And what I can say is that, as we move forward, we'll start holding task meetings in earnest as we've done in the past to try and establish workflow and information sharing and things like that. In addition to the deliverables, we've also got budget period 1 ending September 30th this year. So that will, of course, involve the completion of the technical support of the continuation application, which will be due June 30. So we'll also be leaning on all of you heavily to get that document completed as well. So it's a busy year. We will be hosting plenty of conversations and interacting on a regular basis. But again, I just wanted to provide a brief update with where things stand here now, 3 weeks into the new year. So with that, Balian, do you want to get started?
Sure, yeah.
Okay.
Can you hear me well?
Yes.
Yeah, hello everyone. This is Balian Chen. First I would like to give some background of myself. I'm Balian from Los Alamos National Laboratory. Staff member here. My research interests include CCS infrastructure modeling and carbon storage risk, leakage risk assessment, and also machine learning accelerated inverse modeling and forecasting. So in the past few years, I have been working on CCS project, including NRAP, Smart Initiative, and also the regional carbon storage programs, and also the SimCCS project. Yeah, today I'm very glad to have the opportunity to give a brief introduction on what is SimCCS. So SimCCS is an optimization software to support the CCS infrastructure decision making. And the SimCCS team has won the R&D 100 award in 2019. And Dr. Richard Middleton lead the regional SimCCS development. And after he left Nano and started his own company, I kind of take over the responsibility from Nano's end to continue the SimCCS development and to support the both national and regional scale infrastructure modeling work. Okay, so next slide. Yeah, so SimCCS has the capability to model both the engineering and economics across the entire CCS value chain. So this diagram shows the major component of SimCCS package. It include the SimCCS, just like New York State has New York City. So for SimCCS package, it also has a component called SimCCS. So this component is SimCCS is used for the network modeling and optimization. And for SimCCS itself has 3 subcomponents. The first component is called NICO, which is used for the CO2 capture modeling. Basically, this NICO is a database which include the point CO2 point source and associated capture costs. And second component is subcomponent is called CostMAP, which is used for the construction cost service modeling. And CostMAP can be used to identify the likely corridors and generate the candidate network for the SimCCS network modeling. And we have extend the current CostMAP under multiple resolutions, range from 100 meters to 1,000 meters. And third subcomponent is called SCO TI, and this SCO is used for the CO2 storage modeling. And the output from SCO include storage capacity and cost, and the number of wells, and also the injection rate, etc. So the SimCCS, together with these three subcomponents, can help us to identify the optimal infrastructure network, and also help us to find out what is the pipeline build-out scenarios, including the optimal routes, the length, flow rate, diameter, etc. for each pipeline. And it can also give us an estimate of the cost for CO2 capture, transport, and storage. Next, I will talk in detail about each component. So the first component, as I mentioned, is called SimCCS. This component used for the pipeline network modeling. So for the SimCCS, it has multiple modes. The first mode is called the SimCCS CAP, CAP. So for this mode, first we set up a CO2 capture target, and then we will minimize the infrastructure cost to obtain the optimal infrastructure pipeline network. And the second mode is called SimCCS price. So the difference from the capture mode is there's no constraint requiring the capture of specific amount of CO2. And the target is kind of maximize the revenue or profits. So that means infrastructure is only deployed if it reduces the value of objective function to less than 0, which is the profitable infrastructure. So the SimCCS price mode can help us to identify the first movers in terms of which point source should be captured at the early stage. Okay, so the third mode is called SimCCS time mode. You can also call it time from mode. So the SimCCS time can help us dynamically model the infrastructure over time. For this mode, it break up the project period into multiple phases, and each phase has its own set of cost and capacity parameters. And it can be used for scenarios where things change over time. So for example, if people want to understand how the pipeline network evolves over time, basically this SimCCS time mode will help us to understand that. Okay, so since SimCCS team has developed a very user-friendly interface, so as you can see from this figure, for the SimCCS, it has this interface has 3 kind of tabs. Under the tab of data, we can basically select what type of which example we're going to select. So for example, for this case is for Intermountain West case study. So after we prepare all the data, then we can select this kind of data site, and then we can visualize the location of each sink and source, and also visualize the cost service and kind of the network from this tab. And the second tab is called model. So for this, under this model, basically we can choose which mode we can choose for the optimization. So as I mentioned in the last slide, we have 3 modes: the capture mode, price mode, and the time mode. So here we can choose one from these 3 options. So for example, if we choose the time mode, then we are able to set up the capture targets and the related parameters from this tab, and then we can just click on this button, the generate MPS file, and then we can use the solver, which is called Cplex, to solve this mixed integer linear programming problem. So after this pipeline optimization problem is solved, and then we can visualize the sorry, I think I can. Okay, now visualize the results under the tab results. So here, and this is just a snapshot of the optimized pipeline network. So as you can see, it can connect the sink and source. So the source are in the red dot, the sinks are in the blue dots. So as you can see, the source and sinks are connected by the green lines. Basically, the green lines are the optimized pipeline. And the associated parameters, for example, the the length, the flow rate, and also the diameter for each pipeline are saved in a folder called results. Okay, so this is an example of apply the SimCCS timeframe mode for the pipeline network modeling. So this study is based on the has been done for the iWest Intermountain West Initiative. iWest has been developed to address the energy challenges by developing a regional technology roadmap to transition the iWest to a carbon neutral and economically sustainable energy system within the next 15 years. The CO2 source and sink data are all from the public domain. For example, for the CO2 source, the source data from the EPA flight database. The plot on the right-hand side, the top right, shows the initial setup and the candidate network generation. And for the iWest CCS deployments, basically we set up two phases. For the first phase, it starts from 2022 to 2030. The capture target is 80 million tons per year. For the second phase, start from 2031 to by the end of this century, mid of this century. The capture target is 152 million tons per year, which is the total emission within this region. By here, I want to mention that we kind of set up a kind of threshold for point source equal to 0.5 million tons per year. So after we set up all the required parameters for this pipeline network modeling, so the figure on the right-hand side, the two figures, bottom right, shows the optimized routing for each phase. So if you look at the phase one routing, optimized pipeline network, as you can see, only the point source that has the lower capture cost and the source that close to a storage formation will be selected as the first movers to have the CO2 captured and transferred to the storage formation. The reason, basically, this can be supported from the values in this table. So in this table, you can see you will find the capture cost, transfer cost for each phase. So you can see here for the first phase, the capture cost is about $51 per ton CO2. In second phase, the capture cost is kind of higher, right? It's 57. And for the transfer cost in first phase or early phase, the transfer cost is just about $1.1 per ton CO2. For second phase, the transfer cost is significantly high, which is about $2.4 per ton CO2. So, and this is why I say at the early stage, only the point source that has lower capture cost and close to a storage formation will be chosen as the first movers when we deploy the decarbonization kind of projects. So the second plot is the optimized pipeline network for the second phase. So in the second phase, our target is to capture all the CO2 from this region. As you can see, all the CO2 will be captured and transferred to the particular storage formation. So here I would like to mention for Arizona State, and there's no identified solid information for the CO2 storage. So that's why all the CO2 captured will be transferred to the San Juan Basin in Mexico through this kind of main trunk line. And another thing I want to mention here is if you look at this table, the total cost for these two phases. In phase one, the total cost is $12.8 per ton CO2. For the second phase, the total cost is about $19.4 per ton CO2 stored in the formation. So this kind of indication that under current tax credit is the CCS infrastructure kind of project is not profitable. Next, I will introduce the subcomponents for the SimCCS package. So the first subcomponent is called the CostMAP for the construction cost service modeling. So the CostMAP is able to help us identify the likely corridors and help to develop the candidate pipeline routes for the SimCCS optimization engine. So for the CostMAP, it starts from the GIS information. This include for example, the land cover, the information about the river, road, and also railways. This also the existing pipelines, right of ways, and also include the population density. So after we have this information, then we feed them into this kind of subcomponent called CostMAP, and it can help us to generate the construction cost service. If you look at the bottom left, this is the construction cost service that we generated based on those GIS information. So in this construction cost service, the green color corresponds to the high cost service, and the white color corresponds to the low cost service. And so basically, we are under this kind of cost service. If we provide the location for the source and sink, then we are able to generate the candidate network for the SimCCS pipeline network modeling. So currently, we have had a better version of the CostMAP released to public with the most recent GIS data sites. And one other thing that I want to mention here is that we have the current CostMAP are able to generate multi-resolution cost surveys ranging from 100 meters to 1,000 meters. So this is an example of the SimCCS pipeline network modeling under different resolution. So for this case, is under two different, we consider two different resolution, 1,000 meters resolution versus 100 meters resolution. And this is based on the Colorado case study. If you look at the two pictures on this slide, so on the left is I choose the cost service and also the pipeline network, candidate pipeline network, and optimized optimized network for under this 1,000 meters resolution. So here the purple curve, purple lines represents the candidate network. If you look at there's the green curves here and the optimized or identified optimal pipeline to transport the CO2. Similarly, at the right-hand side is the cost service based on 100 meters resolution, and identified candidate network in purple, and optimized pipeline for the CO2 transport. So basically, the total cost for under two different resolutions are very close, or about around $22 per ton CO2 stored on the ground. And the difference is with higher resolution cost surveys, it can lead to finer candidate routes and also a finer optimal pipeline. However, if we use a higher resolution, it will require significant larger computer memory. So when we do this kind of modeling work, we need to choose a appropriate resolution based on our own computational resources. The second subcomponent is cost SCOT for the CO2 storage modeling. The SCOT can help us to rapidly calculate the realistic injection, storage, and associated costs. And an output from the SCOT tool include the dynamic injectivity, the storage capacity, the plume dimensions, and also the associated economics. And the figure on the right-hand side is an estimate storage capacity and costs for the SECARB region based on the SCOT output. So if you look at this picture, the height of each bar is proportional to the storage capacity estimates, and the counter is proportional to the weighted storage cost. So basically, the green counter corresponds to no cost, which is less than $5 per ton of CO2 stored. The red counter corresponds to high cost, which is larger than $25 per ton of CO2 stored. So currently, we have a better version of this SCO tool released to public, and it is in Python version. The third subcomponent is called NICO for the CO2 capture modeling. So NICO can help us to understand the commercial scale capture utilities. Basically, it is a geodatabase including the CO2 source locations, the CO2 streams, and the associated capture costs. The figure at the bottom left shows the CO2 emission for the 16 categories across the entire US. Yeah, so the data basically are from the EPA GHG flight database, and also including the data from the EPA A-grade. Yeah, so if people are interested in just a particular state, for example, of Pennsylvania, then we can generate a map like the bottom, the top left for the CO2 emissions, and also we can output the CO2 capture cost for each type of emissions. And you can look at the figures at the bottom right, which is the CO2 capture cost for different type of emissions. Yeah, last but not least, so it's about the environmental and social modeling capability. So this is a joint work by NANO and Resources for the Future. So we have developed, we have been developing this kind of capability. So the objective of this work is to add the capabilities to SimCCS modeling framework that incorporates environmental and social impacts on the CO2 pipeline routes. So this work is still under development, and we anticipate this work will be finished by the end of this month. So for this particular capacity, so we add additional layers into the CostMAP. So originally, in the original CostMAP, we only consider the layers include the land cover, slope, population, roads, railways, pipelines, etc. So when we if we want to consider the impact from the environmental social considerations, then we need to add. In this case, we add, for example, if we want to understand how the travel lanes will impact the pipeline routing, then yeah, we will include this information in our cost surface generation. And we also include the 3 different type of protection areas, and also the parks and the critical habitats in our cost surface generation. So after the cost surface are generated by considering the environment social layers, then we compare the SimCCS results with without the environment social considerations. So next I will present some preliminary results based on our current study for the environmental and social modeling. So the figure at the top shows the candidate network in purple, and the optimal path or pipeline in green, without the consideration of the environment and social factors. And the figures at the bottom shows the candidate network in purple and the optimal network in green, with the consideration of environmental and social factors. So as you can see, the candidate and optimal network are very sensitive to the environmental social considerations. And yeah, so the figure on the right kind of the explanation of why the optimized pipeline is kind of have some significant difference. So the figure on the right shows the black areas shows the factors that shows the areas for the environment and social considerations. So the red curves shows in this plot is the optimized path that without consideration of the environment and social layers. The blue one shows the optimal path considering the environment and social layers. So as you can see, the blue optimal path kind of significantly avoid the environment social sensitive areas, for the red one, it kind of go straight from the top to the bottom, and it kind of goes through a lot of kind of sensitive areas. So this is not what we want to see. And yeah, the implication from these studies. So basically, we sometimes lead to increase our pipeline development cost. So in this case, so if we consider the environment and social layers, the construction cost is about $93 million. If we don't consider this impact, the construction cost is only $19 million. So yeah, if we want to avoid this kind of environmental social impacts, yeah, we have to increase the construction cost to avoid these kind of sensitive areas. Yeah, this is just some preliminary results. Now we are extending this work to a larger area and see whether we are observe the similar kind of things. So in terms of the application of SimCCS, currently SimCCS has been leveraged for 3 regional carbon storage partnerships, including the SECARB-USA, and also used in one of the energy transition initiative for the SimCCS, for the CCS infrastructure modeling, iWest, which is iWest. And now NANO is also supporting the FECM national scale pipeline network modeling in coordination with the NAMS team led by Jose. So for this one, we are trying to have an understanding of a national scale pipeline network and how pipeline network evolves over time as decarbonization deploys. Yeah, last I want to talk a little bit about the SimCCS distribution. So overall, the SimCCS, all the components is open source. And so now we have a SimCCS website. Yeah, you can see yeah, this is the website for SimCCS, and you can also find the GitHub link from this website. So for the SimCCS, yeah, one thing I want to mention now for all the 3 modes, the capture mode, the price mode, and also the temporal model for SimCCS is now is available to the. I mean, if people want to test that, yeah, they can find this the source code from this website. Yeah, that's all I prepared for this kind of introductory of the SimCCS.
Okay, well, thanks again, everyone, for your time. As I said, we'll post this information, and I think, if you have any questions, please feel free to reach out to me directly or anyone at SSEB for that matter. We will be scheduling more meetings here to talk about Task 4 in earnest, and some of our partners here are still, working towards onboarding with us too, and we'll be in contact with you as well. Okay. Thanks everyone, and have a great day. And thank you again, Balian. We really appreciate it.
Yeah, thank you. Have a good day. Bye-bye.
Bye.